that we are going to take today examples on optical detector here. So at end of this session, students will be able to calculate the performance parameters like quantum efficiency, responsivity and long wavelength cutoff frequency. So before starting to this quantum efficiency and responsivity, so just recall what is the principle of an optical detector. As we know that there are only two sources, that is the lasers as well as the LED here. So when we are going to generate these lasers and the LED, so you are going to transmit the data using this. So at the detector side, if you want to get the original signal back, so we have to get the original signal by doing the demodulation. So at the demodulation, so when maximum number of light is going to incident on the PIN diode, that is the eccentric material is used, or the avalanche photodiode or the phototransistor here. So more and more number of electrons and holes pair will be generated. Okay, and that is being connected in the reverse manner here. So whenever the light is going to be incident on that, more and more number of electrons and hole pairs get attracted towards the positive and negative terminal of the PIN diode here. Okay, so from those we need to calculate the quantum efficiency and the responsivity. So only quantum efficiency can't determine the efficiency of an detector here. So we have to calculate the responses of the detector here, how fast it is, the sensitivity. So whenever there is a change in the input, the output also we change accordingly to that here. So to calculate the quantum efficiency, so it is defined as the ratio of number of electrons collected, that is output. So whenever you are going to incident the light, on the detector, so the number of electrons will be generated, that is electrons and holes pairs to the number of incident photon, that is efficiency is equals to RE upon RP here. Okay, so the performance of an photo reactor is measured in terms of responsivity, which is given by R equals to N Q lambda upon H into C here. Responsivity, if you see this, that is the directly proportional to the quantum efficiency of a particular wavelength here. Okay, so this quantum efficiency and the responsivity is calculated now. So to understand that, we will take one example on this here. Okay, so we will now solve this example. Okay, so what this example will say, a PN diode has a quantum efficiency of 65% of photon of energy 1.52 into 10 raised to minus 19 joules here. So calculate wavelength at which the diode is operating, okay, lambda, and the optical power required to achieve a photocurrent of 3 microamperes. So when the wavelength incident photon is calculated as in a part A here. Okay, so how it is calculated? So at which wavelength at which the diode is operating. So to understand that, at which lambda is you are going to calculate here. So for that we need to understand that E is equals to HF here. So when detector means what, we are going to incident photon, this is EG should be okay. So this is E1, E2, holes and electrons get separated here because they are connected in the reverse manner here. Okay, so this is calculated here, but F, you know that it is calculated C by lambda here. Okay, if you substitute this H into C by lambda here, so they have given the energy, that is 1.5 into 10 raised to minus 19 joules here. Okay, so you can substitute this value, that is 10 raised to minus 19. H is the Planck's constant, that is given by 6.64 into 10 raised to minus 34 into 3 into 10 raised to 8 meters per second. That is the calculation of an C, that is velocity of light, and this is lambda here. Okay, so lambda is equals to 6.64 into 10 raised to minus 34 into 10 raised to 8, 1.5 into 10 raised to minus 19. Okay, so if you calculate this, it comes to be 1300 nanometer. Okay, so it comes to be an 1300 nanometer, 1300 nanometer here. So this is the part A here, that at which wavelength the diode is operating. So diode is operating at a wavelength of 1300 nanometers here. Okay, so now we need to calculate the optical power required to achieve the photocurrent of 3 microamperes when the wavelength incident on the photon is calculated as in a part A here. So for that so we need to now understand. Now responsivity is, we have seen in the previous slide, responsivity is calculated in efficiency, that is E into HF here, that is efficiency is given 0.65% here. So it is given 65%, it will be 0.65 into 1.6 into 10 raised to minus 19 here. Okay, so and HF here, so HF is calculated, that is be 1.52 into 10 raised to minus 19 here. Okay, so it comes to band 0.64 amperes per watt here, that is the responsivity. Okay, so P in is equals to, that is sorry, P in not here, so we need to calculate the what, R is equals to I photon current upon, because they have calculated to tell optical power required here. Okay, so it will be P in here. Okay, so P in is equals to I photon upon R here, so which is given as an 3 microamperes into minus 6 upon R. We have calculated R here, which is 4.38 microwatt here. Okay, P in, that is the optical power we have calculated, that will be 4.38 here. Okay, so this is one example we have shown to calculate the responsivity. From that we have calculated the responsivity is calculated in this formula also. Okay, so now let us understand one more, that is APD, avalanche photodiode, that is quantum efficiency of an avalanche photodiode is, that is the avalanche photodiode is 35% here. So you tell me, calculate the multiplication factor if it is produces the output current of 6 ampere for incident optical power of 0.35 microwatt here. So M, so multiplication factor is calculated by multiplied output, that is the photo current, upon initial or primary of photo current multiplied. Okay, that is the I output upon I photon. Okay, which is I photon we have, that is R into P in, that we have seen in the previous video here. Okay, so that can be calculated, HE means N efficiency into lambda upon HC. Okay, so into P in, so we have, that is why I photon here. So therefore M is equals to I output upon I photon, that is I output upon I photon. So I photon is R into P in also, so that can be written as an efficiency H lambda HC into P in. Okay, so that can be written as an I output H into C efficiency E lambda into P in here. Okay, so we need to substitute all the values of this formula into this here, so that will be calculation of an M here. So that is the 6 into 10 raised to minus 6 amperes into 6.6, that is the Planck's constant minus 34, into C, that is 3 into 10 raised to 8 meter per second here. Okay, so 0.35, that is the efficiency, which is given by the formula. Efficiency E is what? 1.6 into 10 raised to minus 19. Okay, 1 A lambda, what they have given, 1300 nanometers here, 1300 nanometers 10 raised to 9. Okay, so if you calculate this, it will be 46.6 here, 46.6 here. So your multiplication factor is coming to be an 46.6 here. Okay, so if you see the quantum efficiency of an avalanche photodiode 35, so calculation multiply, it produces the output current of this to the incident. So the multiplication factor is 46.6. If you use PIN diode here, so you will require more and more eccentric material here. So if you make use of an avalanche photodiode principle here, your multiplication factor will be 46.6 here. Okay, so by this we can understand the quantum efficiency and the responsivity of an optical detector here. Okay, so these are my references. Thank you.